Hi, I'm Dan from UConn HKN, and today we're going to be doing another op-amp problem. In this case, what we're trying to do is figure out V out as a function of Vn. So right here, I wrote the top two. Up here are the two op-amp rules. The number one, input currents are zero, meaning that the currents going into these two terminals are zero. You don't have to worry about current going into the op-amp itself. And the two op-amp inputs have the same voltage. So these two have the same voltage. These two have the same voltage. The way I like to think about it is that the positive forces the negative to be the same voltage. That's just how I personally remember it. So let's get started at the beginning. So right here, as I wrote, this is our input voltage. And because our input voltage is just connected straight to the positive input, this is also Vn. So that makes our life easier. So we're going to start writing our KCL equations. So Vn over 1 k ohm, because of here, this is ground, so it would be Vn minus 0, plus Vn minus V1 over 3 k ohms is all equal to 0. That's because of this branch here. Now you do your algebra, you have a fun time doing that, and you find that V1 equals 4Vn. Well, that's all fine and dandy. Now with V2, we have to consider this branch, and this branch. So it'll be three terms. So we see a V2 and V1 here. However, V2 is 0 volts, which makes our lives easier. Because right here, positive input is 0 volts, it's grounded. So V2 is 0 volts. So here we'll have 0 minus V1 over 10K. So it'll just be negative V1 over 10K ohms. 0 minus 2 over 5K. So plus negative 2 over 5K ohms. And here, it'll be 0 minus V out over 2K. So plus negative V out over 2K ohms. And so here, we're going to do some more algebra. When you solve these out, you get V out equals negative 0.2 Vn minus, or sorry, not Vn, V1 minus 0.8. So I'm just going to box off these two KCL equations that we found. So now that we have our equations, the next part is to think about saturation. So we'll consider first the bottom op-amp. No, scratch that. Yes, sorry. All right, so we'll consider the bottom op-amp saturating. So if V out can be at most 10 volts, so we'll do 10 equals negative 0.2 V1 minus 0.8. So yeah, 10.8 equals negative 0.2 V1. You do your algebra, and you end up finding that for it to be 10 volts, V1 has to equal negative 50.67 volts. That's not possible. At very most, or at very least I should say, V1 can be negative 5 volts. It'll never ever be negative 50. So we don't have to worry about B positively saturating. So let's worry about B negatively saturating. So negative 5 equals negative 0.2 V1 minus 0.8. In this case, V1 would have to equal 21 volts. And as we can see, V1 will also never ever equal 21 volts because it can at most be 10 volts. So we know that this op-amp, op-amp B, will never saturate. We don't have to worry about that. However, now we do have to think about the saturation of A. So we'll first consider negative 5 volts, because we know this relationship here. So negative 5 equals 4Vn. So this will happen if our Vn is less than or equal to negative 1.25 volts. And next, we have to think about the other side of saturation. So if it's 10 volts. So this one will cap out at 10 volts. So 10 equals 4Vn. And here we have Vn equals 2.5. Is less than or equal to. Sorry, folks. It's greater than or equal to 2.5 volts. Now, the way I remember these less than and greater thans is here, I imagine something higher than that. So if Vn is, say, 10 volts, so 10 times 4 would be 40, and it can never reach that, so it'll max out at 10. That's how I remember, because sometimes I get confused with these less than or greater thans. So I'm going to write some equations for the voltages we can take. So for op-amp 1, for V1, we get it equals negative 5 volts if Vn, I'm just going to be rewriting pretty much what we got here, between negative 1 is less than negative 1.25 volts. It is 4 Vn if Vn is between these values. Now, this is the linear region. It's the region between the two saturations. This is when you'll usually be using op-amps practically for amplifiers. So if it's in between negative 1.25 and 2.5, it's linear, and we could use it as a nice amplifier. And it'll equal positive 10 volts if Vn is greater than or equal to 2.5 volts. So that's our V1 taken care of. Now, for our output voltage, we remember this relationship, these two relationships we found. So I'm going to kind of cordon off a little area for us here. I'm just going to substitute into here. So we get V out equals negative 0.8 V1 or Vn minus 0.8 volts. Now this happens in if this one is operating linearly, because in that case, this is when this relationship will hold true. So the conditions are the same. So this whole left half of if V1 is whatever values, that's the same for V out as well. So if Vn is less than or equal to negative 1.25 volts, if negative 1.25 Vn 2.5 volts, and if Vn is greater than 2.5 volts. So what we found here by substituting these two, this is our middle case if they're acting linearly. So if our first one is linear, not saturated, this relationship will hold true. We'll get V out is our negative 0.8 V in minus 0.8 volts. Now we'll consider our extreme cases. So if we have our Vn as negative 5 volts, so V out equals negative 0.2 times negative 5 minus 0.8. And so this will yield us an output voltage of 0.2 volts. And finally, our last case, if we are at, wrote that in the wrong spot. Nope, I was right the first time. Sorry, folks. In our last case, we're going to put in if our V1 is equal to 10 volts. So we'll have V out equals negative 0.2 times 10 minus 0.8. And so with our math, this ends up being negative 2.8. And yeah, that's all there is to it. So these are our final relationships for V out when related to Vn. So quick summary. What we did here is we first figured out the KCL equation for op-amp 1. Then we did the same for our second op-amp and figured out these relationships. Then we had to figure out when they saturate. So what input voltage is required to make this saturate at 10 volts and at negative 5 volts, and what voltages are required to make V out saturate. And we figured out V out can't ever saturate. And so then right here, this is exactly what we did, and pretty much plugged in these saturation values of V1 right here, and our linear region is only occurring in between negative 1.25 and 2.5 volts, and only then will this relationship, where they work as an amplifier, a linear amplifier, actually hold true. So that's it for this video, guys. Good luck on Circuits 1.